All of us have heard stories of how a mother, in order to save her baby, is forced to send it floating down the river in a basket. If we take the baby by itself, it will not float in the water. The wooden basket, on the other hand, floats by itself. But when we put the baby in the basket, together they float. How does this happen? How does putting the baby in the basket make it float, even though there is an increase in the total weight? To understand this, we must go back 2,200 years. All those years ago, a man named Archimedes was the first person to think about this. Legend has it that Archimedes was in his bathtub when he noticed something interesting. Archimedes noticed that when a body is completely or partially immersed in, put in water, it experiences a loss in weight. That means the body feels lighter. Archimedes reasoned that this was because the liquid, in this case water, exerted an upward force on the body. He called it the buoyant force or upthrust. He even came up with an expression to give the value of this force. He said it is equal to the weight of the water displaced by the body. Now, these observations form the crux of what is known as the Archimedes Principle. If a body is placed in water, there are primarily two forces that act on it: its weight downwards and the buoyant force acting upwards. Now, for a body to float, the buoyant force must be greater or equal to the weight of the body. According to Archimedes, however, the buoyant force is equal to the weight of the water displaced by the body. So, the weight of the water displaced by the body must be greater or equal to the weight of the body. Now, this statement right here is what is known as the law of flotation. In order to get a feel of this thing, let's consider a body placed in water. Now, the body displaces the water. What that means is that in the place where there was originally water, now the body occupies that volume. According to Archimedes, it is the weight of this displaced water which is equal to the magnitude of the buoyant force. And if this weight of the displaced water is greater or equal to the weight of the body, then such a body will float. If all this sounds a bit confusing, then you don't have to worry, because there is a far easier way to understand the law of flotation. An easier way of understanding the law of flotation is by density comparison of body with water. The density of body must always be less or equal to the density of water for it to float. Density is nothing but the mass per unit volume. With units of kg per meter cube, it is denoted by the symbol rho. The density of water is 1000 kg per meter cube. That just means that if you have a cube whose sides are all 1 meter, the water in this cube would weigh 1000 kgs. Similarly, the density of wood is almost 500 kg per meter cube. That is almost half of the density of water. That means even big structures like the houseboats made of wood in Kashmir would float in water. Consider the gas planet Saturn. It's made up of gases. Now, gases are inherently a lot less dense than water. So if you could find a way to put Saturn in water, it would float in water. That seems surprising, but it's true. You may also have seen pictures of people floating easily in the Dead Sea. That is because due to high mineral concentration, its density is greater than normal water. So it's easier to float there. Talking of density, let's consider steel. Now, steel has a density that is almost 8 times greater than water. Even if that is the case, there are huge ships that are made of steel which still float in water. In order to understand how this happens, let's take a look inside the ship. Now, the inside of a ship has a lot of free and empty space, which is filled with air. Air, being a gas, is a lot less dense than water. Its density is almost 1,000 times less than that of water. So it more than compensates for the high density of steel. That means if you take the average density of the ship, that is, you take the total weight of the ship divided by its total volume, and you know that a large part of the volume is occupied by air. So the average density comes out to be less than that of water. What this means is that if the space occupied by the ship is assumed to be completely filled with water, it would weigh more. So the average density of the ship made of steel, but its volume mostly filled with air, is less than that of water. This also explains why the baby and the basket float together. This is because the water of an equal volume would weigh more than the baby and the basket together. So you need to get rid of the idea that to be able to float depends on how big a thing is or how much it weighs. The only thing that matters is if it weighs less than an equal volume of water, which is the same as saying that it is less dense than water. Take a look at this ice cube which floats in water. A part of its height is submerged in water, while rest of it is above the water. Can we use the law of flotation to find this height which is inside the water? Let us say that the ice cube has sides equal to 1 centimeter, 0.01 meter. Let y be the height of ice cube inside the water. So the height outside the water will be 0.01 minus y. The density of ice is known. It is 917 kg per meter cube. Now, according to the law of flotation, we must balance two forces, the weight of the ice cube and the buoyant force. Now, let's find the weight of the ice cube. It will be given by the mass into the acceleration due to gravity. Is there a way of finding the mass if the density is known? Yes, it is. Density is m by v, so m will be equal to density into v. So we multiply the density of ice into the volume into g. That means 917 into the volume into 10. The volume is 0.01 cube. Then multiplying this will give us the answer of 0.00917. Let's come to the buoyant force now. According to Archimedes, it is equal to the weight of the displaced liquid. That means the density of water into the displaced volume into g. Now, density of water is 1000. When it comes to the displaced volume, we know that the height of the water that is displaced is only y. So the displaced volume is y into 0.01 into 0.01. Multiplying all this gives us just a value of y. Now comparing and equating the buoyant force and weight gives us y equal to 0.00917 meters or 0.917 centimeter. So more than 90% of the height of the ice cube is submerged. Let's apply the laws of flotation to another problem. Say you're a famous scientist who made an awesome chemical, but then you realize that some people are about to steal it. Now you want to hide the formula. Your only option is a lake, which you see. You can seal the formula in a container and throw it into the lake. In your lab, you find two containers of the same height but different radii. Container A has a radius of 2 cm while B has a radius of 7 cm. You also find that A has a mass of 1 kg and B has a mass of 1.5 kg. Now you need to know which one of them would float safely. Let's consider the cylindrical container placed in water. Let R be its radius, the height be equal to 0.3 meters, and we want that at least half of its surface should be visible above the water. Now the buoyant force is given by the weight of the displaced fluid, which in this case is water. That is given by the density of water multiplied by the displaced volume into the acceleration due to gravity. In this case, the density is 1000, but the displaced volume is only half the volume of cylinder. Volume of cylinder is pi r square h, so we need to take half of that. If we multiply 1000 into the half of volume of cylinder into 10, the acceleration due to gravity, we get the expression buoyant force is equal to 4710 r square. Now, according to the laws of flotation, the buoyant force must be greater or equal to the weight of the body. Let's consider the two containers A and B. Now A has a radius of 2 centimeters and the mass of 1 kg. The weight is mass into g, that is 10 Newton. So applying the condition 4710 r square is greater than 10 gives the radius must be greater than 5 centimeter. But that is not the case. The radius is just 2 centimeters, so it will not float. Applying the same condition to B with a radius of 7 centimeters, a mass of 1.5 kg, the weight will be 15 Newton. Applying the condition of buoyant force greater than weight gives that R must be greater than 6 centimeters, which is the case because R is 7 centimeters. There you go, you saved the professor.